we can continue this conversation. All right. In theory, we should be live. But where in Canada are you from?
Yeah, I grew up in Windsor, Ontario, just a small town actually just outside of Windsor. And did my undergrad degree in University of Waterloo in Canada.
Oh, okay. Okay, sure. Yeah, so that's how you became familiar with snow.
That's right, exactly. Yeah.
Well, well, we on the West Coast have just like no idea what this stuff is. So, and we'll
Yeah, it's pretty
never.
special. White stuff comes down from the
Yeah,
sky
yeah,
and
yeah,
turns
exactly.
out to be prevalent in the solar system.
Yeah, yeah. And we'll never actually, I say that, and yet we just had the worst winter. Must have had 4 feet of snow where I live, which is completely unusual. So, yeah. So every now and then, we do get, mostly we have snow-free winters, mostly, but then every now and then we get punished and reminded that yes, indeed, we are Canadian, and this is what we need to expect. So,
Excellent. Yeah.
okay. So who are you? What do you do?
Yeah, my name's Jason Hofgartner. I'm a planetary scientist, and I like to focus on active processes, so things that are actually, happening today. We can see them with our spacecraft, what's happening, and basically for the geology of worlds in the distant solar system. So places that tend now to be known as ocean worlds because they have subsurface liquid water oceans under their surface. They're also called icy satellites or Kuiper Belt objects. And these are places that have, a lot of similarities to the Earth in terms of geology, things going on, like there's rain on Titan and there's eruptions on Triton, but very different chemistries, all much, much colder, even colder than the Canadian North.
Yeah. Now, you came to my attention because you use sort of one of my favorite keywords, which is Triton. But you've since like done another paper that I just saw as well. So there's like a theme definitely to what you're working on. So let's start with Triton and then we'll kind of shift things around.
Sure.
So I think that NASA made a horrible mistake when they decided not to fund their Trident mission and instead funded 2 spacecraft to go to Venus and none to Io and none to Triton. And the correct answer, of course, was all 4. That you launch them all on
Right.
Falcon Heavy, save the money, double the missions, and launch to all of them, especially Triton. Why is Triton such a fascinating world?
Right. Yeah. Triton really is a special world, and like you said, it's too bad that we're not going, but we'll keep trying. And part of there's many reasons why Triton is really fascinating, but perhaps one of them and my favorite is that it is very young in terms of its surface, and so like I just said, researching active processes, it's very clear that there are things that are probably ongoing today, but certainly have happened recently that have refreshed that surface and what those processes are. Some of them are probably things that are analogous to those occurring on Earth, and some of them are probably, rare or possibly even unique to Triton. And so it's got this very young surface, and the reason that we know it's so young is primarily because it has very few impact craters, and so things throughout the solar system are always getting impacted, getting pummeled by asteroids or comets, that sort of thing. But then they leave this scar on the surface, and then if you have resurfacing, it wipes it away. And so Triton has very few of these impacts. It's also a very bright surface, and that brightness is generally indicative of a young surface. That's true on the Earth, and just kind of true empirically, by observation, what we've learned everywhere. If a surface is just kind of left alone, it will eventually gray by processes in the solar system. So Triton is very young, like I said, and then it's also kind of got this unique flavor in that there's a lot of nitrogen on its surface, nitrogen ice. So 80% of the air we breathe is nitrogen. Out at Triton, it's so cold that air is primarily frozen onto the surface as ice. A little bit in the atmosphere. It does have an atmosphere like ours. And then Triton has this very fascinating history that it is almost certainly a captured satellite or moon of Neptune, and that would make it the largest of any of the captured moons in the solar system. And it is probably originally from the Kuiper Belt. So if you think like an object just like Pluto, that basically that was captured by Neptune and brought into orbit around Neptune, then that's Triton. And that capture process has probably dramatically affected its history. It's probably the primary reason, or one of the primary reasons, for this very young surface. And it probably has resulted in this subsurface liquid water ocean. That's still to be confirmed by, probably future mission observations, but that's certainly very likely that there's an ocean under there. And so there's just a lot going on Triton. It has, this atmosphere, like I mentioned, with hazes. And so, going there, there's just so many things that we could learn. We could understand these processes, this geology that resurfaces, how this works. We might be able to glean. It'd be tough to do, but might be able to learn some things about how it was captured. And that capture event may really be related to some of the early history of the solar system. And so there's a lot there. And then, of course, oceans, liquid water oceans, there's the potential for astrobiology. Certainly, one of the better candidates to look. And so that makes it interesting as well. So it's definitely a rich target.
Voyager 2 made its flyby of Neptune and its moons back in 1989. I remember vividly. Yep. I was sort of in my final year of high school, and it was the newspaper of the day. And subsequently, one of the things that Voyager saw is it imaged the planet. We've seen it, and it sucks. Like, the only good picture that we have of Neptune was taken back in 1989 for a few days, and then that's it. And we all have to use those same pictures again and again and again. And they're mediocre. They're fine, but we could do better. But in imaging the various moons of Neptune as it went by, it was able to see a hint of geysers at Triton. And like, correct me if I'm wrong, but is this the first place that we saw geysers in the solar system? Was at Triton?
That was the first place that we saw icy geysers. Others were seen on Jupiter's moon Io, probably more like, kind of like volcanism erupting on the Earth. But that was the first time we saw it from an icy world. That's right. Yeah.
And what was the evidence for these geysers?
Yeah, so the primary evidence is direct imaging in the images that you mentioned, which actually, it was in 1989, but it was using 1970s cameras and technology, just for even, to drag that out even more. But what was seen in those images was basically a plume, so a column of dark material rising up above the atmosphere. And that went up about 8 kilometers, and then it turned over, and then for about 100 kilometers in length, there was this dark material that was essentially a cloud that was being, that plume being blown over by the wind. And then in different images, there were several different images of those regions taken. You can see using what's called parallax, which is basically just, like with for example, your two eyes use parallax to perceive depth. So you was using the same type of physics to be able to see that this material was above the atmosphere, and like I said, it's about 8 kilometers above. And there's some evidence in some of the images that it also cast shadows down on the surface. And so we could see that this was something that was in the atmosphere. And like I said, in the kind of non-optimal images, we can see this evidence for a plume rising up. It's not visually as great as you would like, but it's there. And so this is something that has to be maintained because there are winds in that atmosphere. And so this must be something that's, going up there now. And
so is that unique then? Yeah. I mean, when I think about Enceladus, I think about the tiger stripes, and they're just blasting water ice out into space. I think about Europa, and I don't think there's much of an atmosphere there. But you're talking about these plumes interacting with an atmosphere on Triton. Is that unique in the solar system that we know of?
That we know of, yeah, exactly. So, like you said, Enceladus, and I mentioned the eruptions on Io. Those are quite a bit thinner atmospheres. Triton's atmosphere, I should say, it's about 1/100,000th as dense or high pressure as ours, and so it's this is a very thin atmosphere. This is much thinner than you'd get at the top of any mountain on the Earth. But it is still an atmosphere that moves things around, and you have these plumes erupting out from there. Yeah, the geysers, what I call plumes, are almost certainly from some type of eruption event.
So how do they compare then to the other cryovolcanism that we're familiar with in the solar system?
Great question. Yeah, and unfortunately, we don't really have the answer.
We should send a spacecraft. Yeah.
Yeah, exactly.
Yeah.
What a great idea. Too bad other people didn't think of that. So they're clearly different from, okay, so Io, I've mentioned a couple times already. Io has what we think of as silicate or like a rocky type of volcanism. So that's, in large part, kind of very generally much more similar to the Earth. Enceladus, you mentioned, has these ice volcanoes erupting, blasting out from its south pole, that are going on for at least decades, possibly much longer, putting out a fair amount of material. On Triton, we don't know what these plumes are made of. So they could be icy, and by that I mean water ice, just like at Enceladus. The amount of material actually coming out of each of them is roughly similar to the whole of Enceladus. So all the jets of Enceladus combined in each of those plumes. Or it could be nitrogen in its ice form. So still ice, but nitrogen being very different from water chemically and geologically. And it could be the nitrogen that does that. And so there is a long-standing hypothesis that was actually one of the originals of how these plumes erupt. It's quite fascinating. So let me take a minute to describe it. The idea is you have a nitrogen ice layer, so solid nitrogen ice, that's quite transparent to sunlight. And so the sunlight goes down through, no problem. Lower down, it gets absorbed, and then it wants to re-emit in the infrared, but that infrared gets stuck on by the nitrogen ice because it's much more opaque. So this is a greenhouse effect. This is basically a solid state greenhouse effect. It's like literally, how greenhouses work with glass, how carbon dioxide works in our atmosphere. And that heating beneath that nitrogen ice, because nitrogen is so volatile, if you give it just the tiniest amount of energy, it wants to do interesting things. So that little bit of heating causes the nitrogen basically to turn into vapor underneath the ice, and that vapor pressurizes and then it explosively erupts into the atmosphere. So that's one of the hypotheses for these plumes. It was the leading hypothesis for a very long time. We have argued that that's probably not it's probably not the best to consider the leading hypothesis. It's probably much more on equal footing with an Enceladus type of eruption, where you kind of have, a more analogous to like an Earth volcanism, where you have heating from below, making molten, maybe, melting liquid that's rising up and exploding upwards. Is another hypothesis. And so we think both are very good hypotheses, and either could really explain Triton's plumes. And so it's exciting. I should add, while we're talking about them, that we observed two. I think there is really compelling, and most people would agree, for 6 of them in the images, although we're not as definitive about that. And then there is streaks on the surface all over the southern hemisphere, that more than 100 of them, that are very likely kind of that cloud that I mentioned, that trailing cloud that was windblown. When the eruption turns off, it probably just settles down to the atmosphere and forms those streaks. And so there's evidence for hundreds of these things. And so Triton, in fact, may be a very active world in terms of these eruptions, among, if not even the most eruptive of the solar system worlds.
So if I kind of understand this, then there could be pockets of nitrogen that are sublimating and blasting this material out as whenever they get warmed up to a certain point, or there is actually a sub-ice ocean, kind of like Europa and Enceladus, that is connecting to the surface via these geysers, and they're sort of translating this this material out into space.
That's right.
Yeah,
you got that right. And there's even a third hypothesis that is much less well studied, but the idea there is that it's nitrogen again, but rather than being powered by the sunlight coming down in, you have Triton's internal energy, the same type of thing that might power the ocean beneath, and that energy is leading to convection, so it's causing the nitrogen material to come up warmly, and then when it cools, come back down. Just when you make oatmeal in the oven, or how on the stove, or how the sun works, and when that warm nitrogen comes up, it may explosively erupt as well. And so that's a third hypothesis that I think is still plenty viable, but definitely needs more study.
But that's also really interesting because it allows for material to shift between layers. You could have some kind of convection. There was actually a paper that just came out today. I don't know if you saw this, that it's possible that oxygen is being pulled into Europa from the surface down to the subsurface ocean, that there's systems that are pulling material back down as well. And that gets even more interesting when you think about, say, Titan, because then you've got this really nice layer of hydrocarbons on top, and then you've got the ice, and then you've got the ocean, and a real need to push organic molecules down into the ocean where maybe really interesting things can happen. So it sounds like, I mean, obviously more evidence is necessary, but it feels now, with all of these different worlds, you're seeing different mechanisms doing different things, that it's not just ocean, ice, geysers, that there's a lot more interesting processes that could be happening depending on the world, depending on its environment. Is that right?
That's absolutely right. Yeah, these worlds, I think world is a good term. It's what a term I like to use, because I think it kind of conveys that, they have this character or personality to them, that there's a lot going on, and they all have similarities, but they have their unique intricacies as well. And it's definitely not simple, like you said. That's clear at this point. All the details of how it works, that's what we're still working on, and it's going to keep keep me busy for the rest of my life, I think, because there's just such richness there. But yeah, there's definitely lots of things happening. And one thing that I haven't mentioned yet is that Triton does have methane in its atmosphere as well, and as ice on its surface. And methane, of course, is the most simple of organic molecules. It's just one carbon atom, but then it's a precursor to forming other organics. And so, what role it has in terms of an organic cycling on Triton, and whether or not it is interacting with liquid water, is definitely a very interesting question as well.
So then, based on our current understanding, I mean, I think, for the longest time, the focus was on Mars. Let's send spacecraft, let's search for life on Mars, back with the Vikings. And then that was inconclusive. And so the shift was, let's follow the story of water on Mars.
Continuing, and it's still part of the focus, but it's clear that there are other worlds that are worth pursuing as well, to varying degrees. And we've already mentioned some of the highest priority ones. Europa, Enceladus, Titan, and Triton, I would say, are among the top of those.
Ganymede.
Yeah, Ganymede's a great spot. Ganymede's probably a much thicker ice shell, so maybe not quite as compelling, but certainly it's worth visiting for sure. And yeah, it has really kind of opened the door to considering the possibility of astrobiology on these worlds, and further out into the solar system, beyond what is maybe typically called the habitable zone, right, where you have liquid water at the surface. You now have liquid water not at the surface of these worlds, but deep beneath. And on Earth there is life in the deep ocean, and so it begs the question: is there life down there? And we don't know the answer, but we can get closer towards it with spacecraft, and possibly approach that answer. And so that is certainly something that NASA is thinking about. And since you asked about kind of astrobiology and where it's going, it's good to say then that the planetary science and astrobiology community has basically just finished a process known as the Decadal Survey, if you're familiar with it, where basically once a decade, the community has a committee that essentially looks at some of the highest priorities for planetary science and going forward in the next decade. And our timing today is interesting, because the next Decadal Survey is expected to be released imminently, as probably a month.
I mean, I knew the astrophysics one had come out, but I didn't realize the planetary one was due.
Yeah, the planetary one is very imminent, and so it will, in many hundreds of pages, address the question that you're talking about, which is, what are the priorities and how have they shifted with the discoveries of the last decade? And it will continue to be Mars, of course, but it will also continue to be these other ocean worlds and icy satellites that we're talking about, and it's going to be very interesting to see that document and what it suggests.
Now, on the channel, when we talk about some of these ideas and some of these missions and stuff, we joke about, a rich aquatic environment, European sea, European whales, space whales, and so on. But practically speaking, how nutrient rich and energy rich is the environment under the ice on some of these worlds compared to, say, the subsurface, the deep sea vents and things like that here on Earth?
Yeah, great question. So, Enceladus, the geysers that we've mentioned, they're erupting outwards, and they are almost certainly sourced from this ocean underneath. Maybe not directly. There may be a lot of change and transfer happening in between, but the original source is probably that ocean, and there is plenty of nutrients in there. The Cassini spacecraft flew directly through that plume and just imaged it, but actually flew through it, and essentially sniffed the molecules, and it discovered all the types of basic building blocks that we would think of, and nutrients, types of Earth's oceans, and it wasn't really capable of seeing much more complex compounds, and so they may or may not be there, but certainly the building blocks, the simple types of compounds and elements that are needed were there. And so there are differences from the Earth in terms of, the ratios of the different compounds, and, they don't all have exactly the same nutrients, but it's, overall, it's not crazy different between different oceans or lakes and oceans on the Earth. And so it's clearly not nothing, to answer your question. Some places maybe even more nutrient rich, maybe too nutrient rich. We don't know. Europa's ocean, another very high priority one. We have not been able to do that type of analysis that was done at Enceladus yet. Maybe the mission that's already planned and being built for Europa, called the Europa Clipper, will be able to do that if it does discover plumes there, and it could be. So it's really exactly the type of question we're asking with our research, and we have models and different ways of approaching this question, but we don't really know the answer for much else than Enceladus. And so that's why getting the observations would be great, because other oceans may be much more devoid of other material, or maybe very rich in it, and so it's a great question for research.
Yeah. So what would it take then to start to get some of these answers? You mentioned the Europa Clipper. We talked about the Triton spacecraft that so far hasn't gotten funded yet. There's the JUICE mission coming up from the European Space Agency. Are any of those equipped to give you the kinds of answers that you would be hoping to see? And I guess what would be ideal if, obviously I don't want to necessarily spoiler alert on the decadal survey, but
Sure.
but what would get you the answers that you need? Landers, probes going into the ice, blank check.
Right.
What's it going to take?
Right. Yeah. Well, my research is focused on these geologic processes and what's going on with the surface. And so Clipper and JUICE and Triton are all going to get me the answers that I'm particularly interested in, at least for the next step, because they are very capable, modern, really going to completely transform our understanding of these worlds. It is, astrobiology is something that I'm certainly interested in and aware of, but is not exactly what I focus on.
Yeah.
But I think those spacecraft are possibly capable. If there is a plumes erupting like at Enceladus, then they are certainly capable of flying through them and measuring their contents, even more so than Cassini was. And so, depending on what they find, it's not inconceivable that there were life in there that they would find it. If not, then they might get us one step closer. And it's kind of a question that we just got to kind of keep going. And they weren't designed. Let's put it that way. They weren't designed for detecting life, right? That's not their primary purpose. And so, a future mission, to answer your question, is needed. And generally in the way these exploration of these worlds goes is that you study them with telescopes, you fly by them, you orbit them, and then you land on them. And so that's kind of the natural next step. And
then you sample return.
And then do sample return, yeah. And in the case of these places, maybe dig down, right, or dig down very deep, or kind of get way down there into the ocean. And so, the bigger the sample you get and the more closer you get to the environment that's probably habitable, the better your chance of, determining what's actually in there. And so to answer your question is more missions, which is often the answer.
Right. Yeah.
But Clipper and Juice are, really wonderful, that are really going to take us a big step forward, and maybe, and certainly will give us lots of surprises.
It is interesting though, we talk about the fact that you're focused on geologic processes, and yet you're looking at ice. When we think of geology, we think of rocks, and
That's right.
and yet you've got these worlds where everything is kind of phase shifted one step. How are ice like rocks, but how does it work differently than rocks?
Yeah, great question. So at these temperatures, it's actually a lot more like, and by these temperatures, I mean, like well below 100 degrees Celsius, way out there. In the case of Triton, the surface temperature is something like 40 Kelvin. So, it's like minus 200, more than minus 200 degrees Celsius. It's very, very cold. Water ice itself is actually much harder than snow or glacial ice is on the Earth at that temperature. And so it is actually a lot more like rock. And then the way it behaves, geologically is different in its details, but basically similar in the overall physics. So, if you smack it with an impactor, it's going to form a crater, and the shape of that crater is going to be a little different, but it's going to form a crater. If you have the pressurized water underneath and you crack open that ice sufficiently, you may be able to, have the water come out like it does at Enceladus. And if you, are on Titan, you have methane that's actually in its liquid form at the surface there, because it's very similar to the Earth in this way, but different chemistry, different temperature, and so we're trying to understand, how that all works. On the case of Titan, for example, you have about the equivalent of 1 meter of liquid. If you were to cover the whole surface, you'd have about 1 meter of liquid. If you were to take that for the Earth, it would be 1 kilometer. And if you were to take all the water in Earth's atmosphere and turn it into water, it would be about as thick as your thumb. Or if you took all the atmosphere on Titan and turn it into liquid, it would be about 10 meters. So there's more in the atmosphere than in the liquid. And on the Earth, it's the opposite. And so, they have evaporation and rain and clouds in both cases. But how much does that change because of those kinds of differences is something that we're learning, and that's really interesting to see.
But here on Earth, with plate tectonics and things like that, the rocks themselves are made of aluminum and iron and silicon and oxygen and all of these various elements. But on, say, a place like Triton, it's hydrogen and oxygen. The chemistry simplifies. How does the chemistry affect the geology?
That's right. Yeah. And it's a very rich chemistry, just like on the Earth. And so, it's, there's so much going on, but it affects it in ways, in many, many ways. I mean, there's such a broad question, but, like if we go back to Triton's plumes as an example, that first hypothesis that I mentioned of this solar driven greenhouse effect causing eruptions, there's nothing like that. That's a good analogy on the Earth.
Right.
And so it's affecting the geology, the chemistry of how nitrogen can have this greenhouse effect is affecting the geology in the sense that it's creating an entire new process that can occur on Triton. And then of course, that eruption affects geology because it's, pushing this material into the atmosphere that can get blown around, and then some of it falls down onto the surface around it. It's causing this cycling of material. And so it can lead to entirely new processes. It can lead to processes that are different in their details, and it can lead to some processes that occur on the Earth don't occur on these places. So, and Enceladus and Europa, like we mentioned, don't have an atmosphere. So they don't have, rain. They don't have rivers eroding the surface. They don't have probably glaciers that are cutting through it. So the geology there is much more dominated by tectonic effects, not plate tectonics, but cracking and fracturing of the surface. And so it's kind of it changes, on Earth, there's a constant competition between all the different geologic processes, building mountains and then eroding them down. And it changes the equation of, which processes are winning and which ones are dominant and that sort of thing.
But as you get colder, like say as you go out to Pluto, then suddenly then you almost go to another phase change. Now the nitrogen is forming glaciers and moving and shifting
That's right.
and so on. So do you sort of see how is it almost like places like Triton, like the middle solar system is almost like the tropics of ice, and then as you get out to Pluto and beyond, then it changes again.
There's definitely a gradient across the solar system, and that's part of what makes each of these places, have their unique flavor. Pluto has glaciers and it's nitrogen, and so an interesting example of how that changes the geology. Our glaciers on the Earth, they are water ice on top of rock, and when the water melts, it sinks to the bottom of the glacier and helps the glacier move. It helps erode things. Nitrogen on Pluto is on top of water ice, and that nitrogen is more dense than the water ice it's on. So on Earth you have water ice that's much less dense than the rock it's on, and on Pluto you have nitrogen that's more dense than the ice it's on. So that means it's actually trying to kind of not only like just flow like the Earth like by gravity, but because of density, it's actually trying to get underneath that ice.
Huh.
And then what's interesting is that if you ever did get melt, for example, in those glaciers on Pluto, that liquid nitrogen wants to rise. Water is actually rare in that ice floats. Most materials, if you freeze them from the liquid form, the solid sinks. So on the Earth, you have the water go down at the base. It does kind of this weird erosion. It causes the glacier to move more. On Triton, on Pluto, you might have, that the liquid moves up to the surface, does things on the surface, doesn't actually change how it's interacting at its base. Completely different type of physics, but, glacier doing interesting things in both cases. It's very, very interesting difference.
And do you think that like if you got colder, like, one of the ideas for say Oumuamua was that it was a nitrogen rock, a nitrogen asteroid, as opposed to, so if you got even colder to the point where things like, I don't know, hydrogen are starting to freeze, what could geology look like at that point?
Probably very different again, right? Yeah, and so nitrogen may form kind of one of the limits in our solar system, or certainly what we've explored with spacecraft. A hydrogen world, might be hard to do because hydrogen is so light that basically even given the tiniest amount of energy, it may not stick around. And so the idea of like a hydrogen glacier forming on a world is fascinating. I mean, maybe it occurs in some extremely distant realm from stars, but it may only be very short-lived because, like I said, once you give the energy, the hydrogen may just disappear. But it's an interesting question. Yeah, and it's good. It's a good question to know. Like, is nitrogen kind of the limit for this type of thing? Because we're at 40 Kelvin. It's minus 230 Celsius. There's not much more things that are much more. Carbon monoxide is kind of with nitrogen. So that's another interesting question, or part of what we were talking about earlier. The differences in geology. It's essentially exclusively H2O, water. There's certainly a little bit of organics and dust and that sort of thing mixed in, but it's basically H2O. And so it may be actually that on Pluto, there's this bit richer kind of variance and change. And similar idea for Titan is that the liquid at the surface is liquid methane and ethane. And so, they're probably a much more balanced mix between them. So on the Earth, you have fresh water and salt water, but salt water is still almost exclusively water. It's like 1% salt. On Titan, you have much bigger mixes. And so what does that do interesting geologically? It's really fascinating what it could mean.
And even, when I think about, say, even lava on Earth, we get like the viscosity of the lava depends on the I guess the chemistry of the rock that went into it, and that will sort of define the temperature and define whether you get like the crunchy like the stuff that kind of looks like rolling boulders, or you get the very soupy stuff that flows quickly. Do we think that maybe there's a similar situation going on with different chemistry and the different kinds of cryovolcanism? Do you ever get like lava flows, or are they all just sublimating directly?
Good question. It's there's not really been a lava flow of of icy material that's been observed yet. There's evidence for some of these, or at least they've been interpreted as past lava flows. But on Enceladus, we've seen the geyser, the eruption. It's blowing material well above the surface. We haven't actually seen the equivalent of like a water kind of gushing out onto the surface and flowing out like volcanism on the Earth. And so whether or not that happens is still kind of a bit of scientific debate. But the chemistry clearly affects it. And one thing that I haven't mentioned yet is that for example, like I did say, is that ice floats, right? And that's actually relatively rare, that the water wants to go down, not up. And so that may actually make volcanism on all of these worlds, although it does seem to occur, much less prevalent than it did on the Earth, because simply when you melt, the equivalent of the rock, the crusty material, rather than wanting to rise like it does on the Earth, it actually wants to sink, because that's the behavior of water. And so volcanism may be less prevalent there. Getting access to an actual like flow of water material would be really fascinating to do, to be able to sample that and see what it's telling us about what's going on inside the volcano and inside the interior of that world.
It feels like Titan is probably one of the only places that you might be able to see something like that, just with the thick atmosphere and conditions. It doesn't sound like there's a lot of places where it wouldn't just sublimate off into space with the low pressure.
Maybe, yeah. I mean, it's certainly, the thick atmosphere allows you to actually cool it much quicker. And so it may be that it stifles it, or like you said, maybe it, because there's the pressure there, it allows for that. So Titan is, certainly would love to see more and understand that for Titan.
Now, what if you go the other, we've been talking about chemicals, stuff that we're very familiar with in terms of like ices and gases and things in various forms in colder, lower pressure environments. But what if you go the other way and look at some of these in hotter, more higher pressure environments, but it's still ice and things like that? I'm thinking about, maybe deep down on some of these worlds where it is hot, but still very icy, because like Enceladus is like mostly ice, isn't it? And what about even like maybe some of the ice giants? Like, what do we think we would be seeing inside a place like Neptune or Uranus?
Yeah, so my research is focused on these icy worlds, and that's why I'm talking about them. And we've seen processes on these types of icy worlds. It's possible that there are like metal worlds. As you go much closer to the sun, rather than having ice there, there's metal, and it's doing interesting geology things. And then as you go deeper down in some of these icy worlds, it gets more like the Earth in terms of its rocky composition and its temperature, like you said, but it's not exposed to an atmosphere, so it could be very different. Probably is very different from the Earth. Maybe much more analogous to the bottom of the seafloor on the Earth. And what's inside Uranus and Neptune? Well, I'm certainly not qualified for that to go there, but it's a great question, and it's certainly the type of things that people are researching.
An orbiter to Neptune would help.
Oh yeah, I don't know that it would, it wouldn't be able to probe like deep into Neptune necessarily, but it would certainly, be able to study Neptune in wonderful ways.
And Triton. Yeah, it couldn't. The point is, it couldn't hurt. We should send one.
And the other moons and rings.
Yeah, exactly.
Lots to do there.
So, I mean, in the last couple of days, we got the announcement that NASA has confirmed 5,000 exoplanets or that scientists have confirmed 5,000 exoplanets, with thousands and thousands of more candidates in the works. Upcoming missions are going to be turning up tens of thousands of exoplanets, possibly hundreds of thousands. A few decades from now, we should probably know of millions of exoplanets. Many of these are going to be icy worlds or have moons that are icy worlds. How do you think that our understanding of what we're discovering here in the solar system extends out to the larger, to the rest of the galaxy?
Yeah, great question. Yeah, the statistics suggest that there's probably, like at least one planet for every star in the galaxy. And so if you take that, statistically, although we haven't discovered them all yet, there's billions of planets out there. There's tons and tons to be found for sure. I think what we're learning is that Earth is special, right? Is that there are a lot of things that are like the Earth, a lot of processes, a lot of geology that's like the Earth, but that are that don't make it quite the Earth. That you don't see all of the processes that occur on the Earth occurring really on too many of these places yet. Maybe we will find that in the future, but we don't see that. And so it's teaching us that there's a lot of activity, just lots happening. Just it's not like these are dead worlds that have just been sitting there for an eternity, but there's a lot going on, and to understand that diversity is, I think, going to be very interesting. And whether or not there are true twins to the Earth, or Earth is truly unique, is the kind of question that we might have a much better answer to in our lifetime. But we're seeing that also, that we don't necessarily need things to be exactly like the Earth to do interesting things, right?
Mm-hmm.
So it doesn't have to follow the same recipe as the Earth to have volcanism. It doesn't have to follow the same recipe as the Earth to have rain. It doesn't have to follow the same recipe, to have other geology like glaciers. And so it's interesting to know too, do you have to have exactly Earth-like conditions to have life or not? These are the types of questions that our solar system can give us. And so there's a very wonderful complementarity between studying the worlds in the outer solar system and studying exoplanets, because they're all kind of teaching us about, what is the varying and diversity of worlds, and how are they all teaching us, about the Earth. And it's clear that the Earth is special. And so, yeah. Whether or not we find another one or not, we should protect ours. That's clear.
Yeah. Especially the ice and the water. We talked about this announcement of 5,000 exoplanets, but James Webb has come online with its ability to see into the infrared. Do you see James Webb playing a role in some of the work that you're doing?
Yeah, for sure. I mean, James Webb is very capable of studying, many different objects, and there are plans to look at, all the worlds that we've mentioned so far. And so it's going to take great leaps and bounds in terms of understanding the chemistry in particular on a lot of these places, in terms of just kind of being able to, in kind of like we talked about, the decades between, when we go to Triton and when we go back, and some of the other worlds that maybe slightly, more frequently, but still not frequent enough. James Webb allows, not the same detail, but to monitor much more often, to look at these things. And so it's going to teach us a lot about these worlds. I don't have particular plans myself for that facility at the moment, to using it, but it's going to do wonderful things, and a lot of my colleagues are working on it for sure.
You're going to be busy with Europa Clipper and juice images.
And still, analyzing a lot of this great data that we have from Cassini and New Horizons. So Cassini at Titan and Enceladus, and New Horizons at Pluto is keeping me busy right now. It's been, of order 5 years since those missions ended, but there's still tons and tons of data to be worked through for them.
What about the Titan Dragonfly? This idea of a nuclear-powered helicopter that's going to be flying around in the atmosphere of Titan. I mean, this is a geology's dream, is to have something that can actually go up close to these rocks. What are you looking forward to from Dragonfly?
Oh, I'm very excited about it. Yeah, it's going to be great. One of the things that I'm really interested in is that it's going to be able to, not only get close, but it's going to be able to look at these rocks from the side. right? So the spacecraft, I mean, we can do that sort of very partially by changing the angle, but we're basically looking down because we're in these, up in space looking down. Dragonfly is going to be able to get up there, and so when it finds a cliff, it doesn't just have to look down the cliff, but it can actually look on the side and see what the character of that cliff is. And so I'm really excited for that aspect of it, especially because it's a helicopter that can fly. It can like pick its height that it goes to, and it can really explore it in a very interesting way. So
what would that tell us?
Fantastic, like you said.
Like if you could look at a cliffside,
yeah,
what would you be looking for as a geologist?
So what I want to see and what I predict will be there is layering, and that layering is basically a record of the history, right? Because each layer was kind of deposited at time, and then the next one got deposited on top. It's kind of the general sequence, and that is so key to understanding the history of the Earth and the geology of the Earth is understanding its layering, its stratigraphy, and despite how important that is to the Earth, it's actually not super common on other worlds. I mean, every world has layering to some degree, but they don't have, like, if you were to go, to a mountainous area on the Earth or any place where you can see lots of layering, we don't see that on very many places. It's Mars. There's good evidence. Mars has that. We know that now, but there may not be many others. Titan probably is one because Titan has this liquids at the surface. It has this rain and rivers. So it's eroding material and depositing it and then eroding it back away. It's probably creating this layering. And so I think that's one of the most exciting things. That's one of the things I'm excited about that mission, because it would tell us that there's this much more detailed record, right? So we're trying to understand history, and we're always learning about the history of these worlds, but if it has this layering, it's recording that in much more detail in terms of time. And so it would be really exciting to be able to kind of take that step to looking at that level of detail, at Titan's history, and to understand if it's had, the types of things like we've had, like variations that are maybe more equivalent to ice ages or, different huge epics of geology. Has it been just kind of Titan the way it is now? Has it been like that throughout all of history, or has it been dramatically different? I think it probably more likely it's been dramatically different, but if we don't know how, and now we could learn that.
Yeah, that would be amazing. I sort of think about places, when you drive and it's cut into a hillside and you can see the various layers that have been
Yep.
laid down over long periods of time. And you're like, each one of those layers has a story of something changed and now you've got, and so you can imagine situations on, say, Titan where, maybe it ate a set of rings and you've got this deposit across the entire surface, or maybe there was volcanism that was layering out, or maybe you had some giant impact that splashed debris and you could just see these. I mean, like a core sample would just be incredible, but I mean, just as you say, a helicopter is going a long way. It's pretty exciting to think about that.
Absolutely.
So we talked about this idea of like 5,000 exoplanets. Now James Webb and upcoming space missions and even some ground-based instruments can start to analyze the atmospheres of these worlds. Next comes somehow studying some sense of the features on the surface of these worlds. How could we maybe get a sense of what's on the surface of some of these exoplanets from such distance? And I know that's not specifically your field, but when I think about what kinds of instruments, what kinds of techniques could give us a sense of what's on their surface, geology-wise.
Right. Yeah, it's certainly the type of questions we want to be able to answer, and so I think the way that progress will be made is by a combination of using things like James Webb to do observations, that is going to really teach us about the atmosphere, and then modeling, and so using computer models to predict based on everything that we can learn about those worlds, what does the surface look like, and the more that we learn about our own worlds in our solar system that we can actually go and touch and see the surface, the better informed those models can be. And so I think that's where we're going to see progress, during the era of this decade of the James Webb Telescope, is kind of this, teamwork between the observations and the modeling. And, seeing the surfaces of these worlds is a very, very, very challenging thing to do. And so that's still a ways into the future. But that's I think how we're going to do. And so it's a lot of kind of layer science, built up that we understand these things and we're putting them all together. And this is our prediction for what that surface is going to look like.
Yeah.
And how can we test that and how can we make that better?
But if I could give you, say, 1,000 planets and give you 1 pixel from each one, a spectroscopic data of 1 pixel of 1,000 planets, would that be interesting to you?
Oh yeah, I mean, of course, it would be interesting to know, like what I mean, the spectroscopy is very useful for getting a sense of the composition, and so it'd be very interesting to know. And of course, finding liquid water is a very interesting question. So it's good. The question is, how confident am I in what I've learned from those pixels, right? And,
right.
So I can understand, the composition on average, which in the case of the Earth, we're roughly 70% ocean. And so, would I be able to know, is it primarily ocean or is there also continents there? And would I have a sense for, is it like, this one giant continent or the ocean? Or is there like, many little pieces of land everywhere and water around? These are all the types of things that you can't really answer well with 1 pixel,
right.
But as you get more, then you can do better. So that's what's.
So would it be more interesting to get time-based pixels or multiple pixels? Like if I could give you those same 1,000 planets, but give you, your data once a year.
Yeah.
Or would it be more interesting to give you 4 pixels?
Well, of course, the answer is both, right? If you if you were to ask, of course, it's both. So for me, for the research that I do, the time is critical.
Yeah.
And so, like we talked about at the beginning, like I'm interested in understanding these things that are happening today, and really, learning what's going on from them by observing them, and then being able to extrapolate that into the past. And so for me, time is critical because time is how we as humans we intuitively get that things are changing, and so there's just so much information that's recorded in those changes in time, and so that's for me in my research, of course, interesting. But like we talked about earlier too, is that there's this great diversity and great variance among all the worlds, and you don't get to appreciate that by just studying one, many different times. You need to really see all these different samples. And so, there's just things that however far we take our science, we won't predict, these things happening until we actually go and see them. There are so many examples of things occurring on Pluto that are, related to what was expected and predicted, but just not even, at all, not even close to like the way it's actually on Pluto, and things like the nitrogen glaciers, like we just maybe there was predictions for nitrogen glaciers, but we just didn't have like that sense for just how they would work and what they would look like on Pluto.
Mountains.
So really got to see them.
Yeah, I mean, even just seeing the pictures of those mountains, and if someone said to you 10 years before New Horizons arrived and said, when you see the first pictures of Pluto, you're going to see mountains made of ice and glaciers made of nitrogen, surrounded by an atmosphere, you'd be like, no, no.
The way I like to think of it, just to interrupt for a second, is that Pluto's moon Charon is about as interesting as I expected Pluto to be, which is to say that Pluto's moon Charon is extremely interesting, and Pluto is just way more than I think anyone really truly thought. It's just it's totally fascinating.
Yeah. Well, it's absolutely fascinating work. So is there a mission to Triton in the new decadal survey? Can you give me a spoiler?
Oh, no, I don't know. I'm not involved in that decision. So I don't even know. It's like I said, it's a committee of people from the community, and it's not, an entire community. As you can imagine, if you asked everyone to agree on what priorities there would be, it would be, it could be quite the argument and debate that would never be settled. So I don't know, but I think what we can say is that it's likely that that Triton's value will be recognized, and whether or not it's that's enough to bring it all the way, say, to a top priority or second priority, or a kind of a deferred priority to a future decade. That we'll have answered in just a few weeks. But I hope it is. That's
Yeah.
for sure.
Yeah. I mean, I think that for the last decadal survey, obviously the big priority was Europa, and just the understanding that these ice worlds are so interesting. But I mean, the ice giants are chronically underexplored, and it's moving into criminal. So, like, at a certain point, a mission has got to go to either Uranus or Neptune, preferably Neptune, because of Triton. Now is the time. So,
Yeah.
hopefully, this round, someone sets aside a few dollars to finally go back. It's weird, like I said, I was in high school the last time we got pictures, and I'm not young. So,
Right.
it's time. It's time.
Yeah, I mean, it's extremely difficult to do. And so, that's part of the reason. It speaks to how hard it is that no one
Yeah.
has done it. But yeah, I think it's worth
Well, we went to
prioritizing.
Pluto, so and we've done it before, so it's still possible. Well, Jason, absolutely fascinating work. Thank you so much for taking the time to chat with me. If people want to follow your work, what's the best way to do that?
Yeah, so the work that we talked about on Triton is published in journal Icarus, so it's easy enough to find on Google. And my publications research are all online. So I'm fortunate to have a relatively unique name, and so
Yeah.
it's not so hard to find me and what I've done.
Yeah, there's a great list. I think on ResearchGate, a few places you can see a list of all the papers that you've been involved in. Some are open access, others are on journals, but you've been fairly prolific, and there's a lot of really interesting science to read about. So if this is interesting to people, they should definitely read more of your papers. I found them really fascinating. So thank you, and good luck. Let me know once the mission is approved. We'll talk again in a month, I guess.
Okay, yeah, I'll look
All
forward
right.
to it.
All
Well,
right.
thanks for
Sounds
having
good.
me. It's
All right.
always
All right.
fun
Take
to
care.
talk about these places.
Bye.
See you, Fraser.